My name's Todd Gooch. I'm the author of the Gravitational Unit Theory, Unified Field Theory. And today I'm just going to draw a couple molecules for you. We're going to start out by drawing some of the atoms. So here's my favorite, hydrogen. It's got two bonding sites, unlike you would see in the standard model. This is supported by Nobel Prize winning work showing that hydrogen bonds to two boron atoms in the cycloboranes, and specifically B10H16. Here we have helium. Vectors coming out each side. Standard model, usually on one side. And on one side, you get two of them, you know. So then we have lithium. Standard model lithium, one dot, one bonding electron. Lithium here, a key and 7 keyholes. And this is why the octet rule exists in chemistry, is that there are 8 general bonding sites on the second and third period elements. Same geometry up here, but really that's just 2 bonding sites. It has to do with size limitations. Beryllium. They usually follow it around in the second period. It starts to go around. For me, beryllium goes like this. And these are all keyholes. Vectors that face away from atoms. Atomic symbols are keys, and vector arrows that face towards the atomic symbol are keyholes. The idea is to fit keys into keyholes to make molecules. Here's boron. With its 3 bonding keys, bonding preference to keyholes. General idea, at least. And so 1, 2, 3. Boron, carbon. Everybody's favorite is carbon, isn't it? I like hydrogen, but most people are carbon fans because of life. And this is how they draw it in the standard model. The idea is it can take on or give up for equally is the idea behind and its life-giving properties. Here we get better idea, description of what's actually happening with the atom. So nitrogen for the standard model is 1, 2, 3, 4, 5 bonding electrons. Nitrogen for me is it's a keyhole element. So these are the bonding sites that you're interested in. Most of the time you would think it, but I'm noticing an awful lot of bonding with the keys in this atom after these keyholes have been filled up. It seems to be that the keyholes fill up over here, and then these things bond in what I call a one-way single bond. It's called lone pair bonding in the standard model. But what you got going on is 2 vectors that are bonding to all sorts of different atoms. Oxygen comes to mind as one, but really higher elements. I'm seeing anything that's got 2 keyholes right next to it. This seems to have an affinity for this type of bonding. So the next one's oxygen. Here's oxygen. Oxygen standard model. 1, 2, 3, 4, 5, 6. 2 lone pairs here. For me, gravitational unit theory, it's 2 keyhole to form the single bonds. These are single bond areas to bond. This is where you would have like hydrogen bonding in water. This would be catching the backside of hydrogen over here to make H3O plus and also the hydrogen bonding in water. Haven't really gotten to any molecules yet. I've been talking about them, but about to run out of time on my video, so I guess it's about atoms today. Here's fluorine. This, of course, looks like this in the standard model. And then what we have here, this is a keyhole element. So there's this keyhole, and then it's got 7 keys. It bonds predominantly with the keyhole, showing that it is actually a keyhole element, and they do work that way. And then finally we have neon. And neon's just all filled up, all 8 here. And for me, it's all vectors going away from the neon atom. It looks like I've got maybe a minute left. I'll try and draw you a couple, or at least a quick structure or two before I run out of time. I like doing benzene because it shows you what the 1.5 bonds are that show the equal energies on the carbon-to-carbon bonds. This would be a 1/2 bond. You can't do that. You can't do that bond in Lewis structures. So this is how you would get your equal energies on each one of the carbon-to-carbon bonds. Now, if I wanted to add let me go ahead and draw these in. It looks like I might have enough time to go ahead and draw them in. And then this gives you your aromatic ring. So we get the aromatic ring in there. And then if you want to make a benzene, we'd have to then put in the hydrogens. And so what we have here is your hydrogen here. So you got a single bond. It's really a half bond because this is not involved in any bonding. You find this later to be very important in the metallocenes, where these all contain a plus charge and they bond to a metal atom. And in the standard model, I'm seeing nothing that's correct on the charges